Hey guys, I just wanted to try and make a quick little video to help us be able to better understand the starting point of Chapter 2 and what the intention is of basically the remaining sections for this semester and also for the homework for this semester or for this section. So hopefully you guys have read through the notes, and really what I want to do is provide some input about some particular things I'm hoping that we're focusing on. So this is the start really of how we will approach group theory. This section you should really notice a change in, let's say, style, mostly because we are switching to learning something new, whereas in the previous sections that we've considered, this has really been more of a review from the viewpoint of if you've had something like calculus or linear algebra, you've hopefully seen proofs and seen logic and all of these ideas that we've used before. Now, in the previous chapter, in the introduction, we had considered three distinct properties that we hoped an operation would have on a set. And these properties are going to show up later, but before we dig deeper in that direction, what we want to do is get a good intuitive understanding of what a group is, rather than simply living in the realm of mathematical abstraction and formality. So, to get us started, basically the idea is to consider something I imagine most of us are familiar with, which is a Rubik's Cube. So the Rubik's Cube is pretty basic. It's simply a cube, and each face of the cube is made up of 9 smaller cubes. Everything is symmetric, and we would be unable to tell the difference between any of the sides if it weren't for the colors. So, with that, we can think of the Rubik's Cube as being a particular object that we want to study. And when we look at the cube, the idea is typically you start to mix it up so that you can attempt to solve it. And in order to mix it up, the idea is you simply rotate the faces in various different orders. And for example, the following picture shows us how rotating the cube or various faces of the cube in different directions can result in different configurations. Now, at the moment, this doesn't seem very mathematical, but this is exactly the type of idea that we want to consider inside of group theory. And in fact, everything that you do in algebra, whether it's the abstract version we're studying or the very simple version that you're teaching your students, even though they make it seem like it's not that simple, is really a study of symmetry. And the idea is almost everything that we do that is algebraic in nature can be reformulated into this notion of symmetry. So starting with the Rubik's Cube is a wonderful way to approach this. So, of course, these first few pages are simply a background on the Rubik's Cube. But here's what we want to do. We want to study this Rubik's Cube or at least for now. And what I want you to consider is not necessarily the cube. I mean, the cube is important. But the important thing that we're going to focus on are the ways in which we can manipulate the cube. So our objects of study won't necessarily be the way the cube looks, although we can relate them explicitly. The idea is our set of objects will be, for instance, rotating this particular face by 90 degrees clockwise, or rotating this particular face by 90 degrees clockwise, or the composition of these two rotations. And so what we can see is all of these ideas are very simple, and they're simple manipulations of the cube, but I want us to focus on the fact that these rotations, or what we'll call actions, are really going to be let's say, our focus in this study. So, moving forward, we said, okay, we're looking at these rotations, and we want to simply endow them with the most simple properties or rules that we can think of. So the first one is the fact that there are a predefined list of rules. And you might say, well, myself and my other group member have a different predefined list because I'm allowing all possible rotations and they're not. And that's perfectly fine. But what we're saying is we want to pin it down in a very explicit way, and there's a predefined list of moves that never change. And the idea is those predefined list of moves are simply 90-degree rotations of each respective face. Now, The idea, of course, is we can define that, and that's perfectly acceptable. However, you might say, well, what if I want to rotate it by 180 degrees? And this is something that we'll get to, and the idea is, well, that's perfectly acceptable. You can do that, but it will be built from these much smaller and simpler things, which are 90-degree rotations. So a 180-degree rotation would simply correspond to doing a 90-degree rotation twice. All right? So we have that there's a predefined list of moves, and these don't change. If I hand you a Rubik's Cube, you cannot create a move that has never been seen before. Now, similarly, every move is reversible, and it's exactly what you think. If I rotate it clockwise, I can simply rotate it counterclockwise to return to the original position. All right? So this seems obvious, but it's something that we want to endow other objects with, right? The Rubik's Cube is our starting point, but ultimately we're going to study things that are far more exotic and abstract. So the Rubik's Cube is a great game because I can undo my mistakes. Further, every rotation is deterministic. Now, this word tends to have a strange connotation because we start to think about statistics or probability theory. But in reality, what I simply mean here is there's no variability in the outcome. If I would like to rotate face 1 by 90 degrees, there is no real chance that, for instance, unless there's an earthquake or something that we're obviously not considering, that I won't be able to do so. The idea is if I decide to rotate it, it simply will rotate it. Whereas if I wanted to flip a coin, while I can, with enough assumptions and enough effort, control with some high probability the face that it will land on, that is not deterministic because I don't have 100% control. So this is deterministic in the sense that there's no skill or luck. I simply decide to do it and it's done. And finally, any move that I want to do can be done in sequence. So what does this mean? If I want to rotate face 1 and then rotate face 2 and then rotate face 6 and then rotate face 1 twice, that is a perfectly valid thing to do. So this is where it's somewhat helpful to remember there is an object under here. So although I'm talking about actions, which are the rotations, what I mean by it's allowable to be done in any sequence means I don't somehow break the cube or end up with something that's not the original Rubik's Cube. So all moves can be done in any particular sequence, and it will not violate the fact that they are simply manipulations of the configuration of the cube. So we've picked something very simple, and we've made 4 great observations. And of course, we could do things more, right? We could say, oh, well, what about the colors of the faces? What about this? What about that? And all of these things would be perfectly acceptable. However, that's not the current goal at the moment. What we want to do is simply construct some very simple and expected observations, and then later we're going to start trying to determine what other objects or sets of actions will have these properties. Now, so moving forward, let's try and generalize this a little bit, and you can see that I'm talking about the study of symmetry, and really the idea is the cube is quite phenomenal, and it's actually the case that different sequences of actions will actually give me the same exact object. And what this means is it implies some notion of symmetry. Somehow if I go one way and then go a different way, I can potentially come to realize, the cube can come to be realized in the same exact configuration. So this notion of symmetry is actually something that is very important. All right. So moving forward, what we want to do is, and this is simply describing why we're going to focus on symmetry and explaining to you some of the things that we'll focus on. So I don't think I need to explain those too much. But what we want to get to is, of course, the formal rules of a group. So what we want to do is we want to take the 4 observations that we just made, and I would like to formalize them a little bit. I would like to basically say, how could I construct these observations to be independent of the fact that I was considering the Rubik's Cube? And you might say, well, I don't know what else I would consider at this moment because we don't have experience in group theory, and that's fine. However, loosely speaking, we understand from the introductory chapter that we can consider things like the integers and the real numbers and integers modulo n and matrices. So there are other things that we could consider. So what we're going to do is we're going to remove the emphasis on the cube. Now, The way that we'll go about doing that is relatively simple. We'll simply construct our 4 rules, and they should really match up with exactly what we just had in the previous section. So, the first rule of a group, which we'll define later, is simply going to be that there is a predefined list of actions that never change. So in a sense, I have a set, and it is a given set, and I cannot take away from it or add to it based on the definition. Of course, we could decide to do that, but the idea is this list is unambiguous, and it is a predefined list. All right. Every action is reversible. Nothing changed here in terms of its definition with respect to the cube. So the idea is if I have a list of actions, there is somehow a reverse of every action. Okay, so that's something very important to understand. Every single action can be reversed. Every action is also deterministic. Nothing has changed here. And any sequence of consecutive actions is also an action. So when we're saying action here, of course, right now we're thinking rotations of a face of the Rubik's Cube, but in general, this will become something more exotic. For instance, not to get bogged down right now, but adding numbers can be an action. Multiplying by matrices can be an action. Many other things can be actions. So the idea is if I have given you a set of actions, they need to somehow follow these 4 rules. So, and this is all we've done in terms of our rephrasing. Now, in the case of the Rubik's Cube, to kind of bring this all together, there's only 6 basic actions. Like I said, what these actions are the rotation of each of these faces by 90 degrees counterclockwise. So let's say action 1 is rotate face 1 90 degrees. Action 2 is rotate face 2 by 90 degrees, and so on. However, we know that there are more complicated actions that exist. For instance, the 180 degree rotation. And so the idea is that the first rule tells us that all actions are generated by these basic 6 actions, and therefore we call those 6 actions generators. Now, I will go into this more later, but here's really what you should take from this. Inside of a group, there will usually be a list of actions that will allow me to derive every other action. And those actions are called generators because they're the basic moving blocks. And another way to think of this is as follows. If you're walking around on the ground, then if, for instance, any of you guys have ever played video games, then you can imagine me walking diagonal is really a combination of going forward, right, forward, right, forward, right, forward, right. Or if my slope is different, it might be forward, forward, right, forward, forward, right, forward, forward, right. So with that, I can generate my movement with those 2 actions. You might say, well, what about left and what about back? Well, back is simply the reversal of forward, so we can just say that forward is my action and I can reverse it. And similarly, right has the reverse left, and so we don't need to really distinguish between those 2 objects. And so what you learn in Calculus 2 or in linear algebra is that you can generate all of the Cartesian plane or the XY plane using only the, let's say, I vector, which is kind of this vector that went in the direction of the x-axis, and the j vector, which was this vector that went in the direction of the y-axis. So every movement in the plane is simply combinations of right and forward. So in that same way, every configuration of the cube is somehow a result of doing a rotation of each face in many different, let's say, orders or numbers of times. So, and this is something to be very kind of clear about. There's only 6 generators for the cube, but if you were to go through and count, there's actually something like, I don't know, I think something like 4 trillion different distinct actions that one can perform on the cube. So there's a very big difference between the number of actions that I can observe and the smallest set of actions that I need to generate them. And this is going to be something important that we discuss later. So if I say that you have these actions, then typically what I'm saying is those are the only things that are allowed to exist. I'm not saying that these are your generators necessarily. All right. Now, of course, I think some of you guys may have different questions depending on the nuances of this, but I'm going to let you think about this and, of course, come to me if you have something specific that you want to discuss. So we have these 4 rules, and this gives us our first definition, which is that of a group. A group is simply a system or collection of actions that satisfy the rules above. Now, of course, this is a terribly informal definition of a group and something that we will rectify later on. But for now, this is our working definition of the group, or a group. And you should not try and use other knowledge that you may have at this moment. So what I mean is you should not be trying to say to yourself, well, I took group theory 5, 10, 20 years ago, and when I took group theory, we defined it as axioms X, Y, and Z. And I'm going to use those axioms to determine whether this is a group. Now, while that's a perfectly valid way to think if it helps you understand, what you should be doing, for instance, in the current exercises, is determining whether or not a set of actions follows these 4 rules. All right. So, of course, this is not a terribly involved chapter, but this is something that's pretty simple, and I want us to really spend some time thinking because it's going to be important to really kind of wrap our brains around these conceptual ideas. All right. There's nothing computational here, and that can be a problem for those of us who, for instance, like math because we feel that it always has an exact correct answer. So this feels a little bit vague. And while it can feel like this, later we'll learn that this is actually still a very exact axiomatic way to do things. It just feels strange because there's no numbers. So what I want to do now is, of course, just briefly describe these exercises because I know that they can be confusing to read. And I'll be honest that the way they're written, there's the obvious, let's say, potential that you could interpret the exercise differently from how I intended you to interpret the exercise. So what I'll try and do is motivate what I am hoping you'll see with this exercise, whether or not you actually see it. So in exercise 2.1, you put a penny and a nickel side by side on a table and consider the simple action of swapping the places of these 2 coins. So what I mean is you've just put these penny and nickel down on the table, and you can do this yourself. And I'm saying that you have the action where you just swap the order of these 2 coins. All right? So, is this a group? So your action's pretty simple. It's just swap the order. So you are not to focus on the actual order. It's simply the action. All right? So do you have a predefined list of actions? Well, I've said you switch the order of these actions. So that seems predefined to me. All right. Is every action reversible? Well, if I switch the order of the coins, can I switch them again? Yes, if you switch the order, then I'm back to the original configuration. So there is the ability to reverse whatever I've done. Is it deterministic? Is there anything unknown about it? No, I'm not flipping the coins. I'm simply choosing to switch the order of them. And then I finally ask myself, is it the case, and of course I think this is the one we struggle with maybe a little bit more, that any sequence of consecutive actions is also an action? So, what does that mean? Well, if you switch the order 57 billion times, that still ultimately boils down to either I switched the order or I did not. Those are the only 2 configurations of the 2 coins. So, with that in mind, it seems to be the case that every consecutive composition of actions is once again an action. So, this is a group, and you just simply need to explain why each of the 4 rules are true. So the idea is, of course, there's no proofs, there's no induction or anything like that. You simply need to logically lay out your description for why each statement is true. Now, exercise 2.2 is pretty similar, except I've said there's a dime to the right of the other 2 coins, but still you can only switch the penny and the nickel. All right? So what you have to think about is, even though there's this other object over to the right of them, my action is still the same. So you have to ask yourself not whether I'm able to move all the coins, right? So I think we'll start to ask ourselves, well, no, I can't move the dime, so I cannot get all possible orders of the coin, or the coins. That's not what we're saying here. We're saying if your action is only switching a penny and a nickel, does the presence of the dime even matter? And if it does it prevent this from being a group? All right? So the answer is, well, of course, this should still be a group, but you need to determine why. Exercise 2.3, you have 5 marbles in your left pocket, and you have 2 actions. You move the marble from the left to the right, or you move it from the right to the left. Now, there are many ways of thinking about this. For instance, you may say, I have no way of knowing whether I'm choosing the red marble or the black marble, so it's not deterministic. That's a valid thing to say. Or you might say, I'm going to look in my pocket so it can be deterministic. Or you might say, they're all the same colored marble, so there is no kind of need to distinguish between them. And all of these are valid ways to think about it. But you also have to ask yourself questions such as, can I move a marble from my left pocket to my right pocket 10 times? And you have to be very careful, right? You have to think, as I'm moving things, it does change what is in each pocket. So you have to ask yourself whether each action is possible. All right? So I'll let you think about that, and hopefully it's pretty clear. 2.4 is another strange kind of situation. You have 3 walls that you can put art upon in your room, and you can't use the 4th wall because it has a window. So what I want you to do then is come up with, or basically study this situation for whether or not it's a group. So step 1 is, of course, if you have 3 pictures and you have 3 walls, how many different ways can you arrange them? This is a simple counting argument that you probably teach your, intro to stats students. I'm not entirely sure when we learn that, but I think it's maybe something like 8th grade. So I'm sure that you at least know a little bit about this kind of construction. Now, consider 2 actions. You can swap the art on the left wall with the art on the center wall, and you can swap the art on the center wall with the art on the right wall. But you cannot directly swap the art on the left wall and the right wall. All right? So that's not a given kind of action. So you have to ask yourself whether this is a group. So you have a predefined list of actions. I think that's clear. You can reverse them because swapping is simply a reversible procedure, just like it was for coins. It does seem deterministic, but then we have to ask ourselves, is every possible, let's say, action that I can come up with an action itself? All right. So we have to ask ourselves whether everything I do can be realized as, for instance, just simply swapping left and right and swapping right and center. All right. So of course, B and C are kind of a combination of what I've just described. And then part D, I add an extra rule, which is simply the fact that I can move all art on the right wall to the center wall, even if there's more than one piece of art there. So then we ask ourselves, is this a group? All right, so once again, is this something that is, able to satisfy each of the 4 rules that we have listed? All right. Exercise 2.5 asks if the last rule implies that every group must contain infinitely many actions. Well, the answer is no, but you should explain to me why it's no. Right? The idea is just because every set of actions or composition of these actions has to be an action in its own right does not mean that these need to be distinct actions. Does that make sense? So there's no need that every time I do something, I get something brand new. Okay? Could be the case that I keep doing things together and over again, yet I'm simply repeating myself. So explain to me why it does not have to be infinitely many actions. All right. And number 6, so for each of these situations from the previous 4 exercises, if the situation described a group, explain to me how many actions are in that group. So this means don't only just count the actions that I've listed or provided, but also determine whether or not there's other things that you could consider. So, so in the first problem, I gave you the action of switching the coins. If I keep switching coins, how many possible different actions can I generate from that? All right. Exercise 2.7 says, once again, consider the first exercise. Only one action was given, and so we can perform that action twice, and that's perfectly valid. What does that action do? So qualitatively, or give me a description of what the switching of the coins twice in a row will do. And then part B says, will every group have an action like this? So I don't mean that if I do something twice, the same thing twice, then I get the result from part A. I am simply saying that if I have an action, will there be, for instance, another action that I can apply so that I get the result from part A? And then 2.8, you simply should give me an example of a group that meets these requirements. So, of course, this will probably require you to do some thinking. But, for instance, the order in which the actions impact the outcome. So what you should think about is somehow there is not this commutativity feature. The nicest way that I like to describe this is as follows. There's a difference between putting your socks on and then your shoes versus putting your shoes on and then your socks. So in that same way, I think you could envision that there are other actions that would be a group in which such a thing could be plausible. For instance, maybe we considered something like that in the previous chapter. And then, of course, the order in which the actions are performed does not affect the outcome. Then that's probably something pretty standard we've seen as well, whether it's in this chapter or the previous one. Then a group with 3 actions. And so what I mean here is not 3 generators, but I mean that if I take every possible way of combining the actions, there are only 3 distinct outcomes. Similarly for the 4 and for the infinite. Now, exercise 2.9 is one that I think that we may struggle with simply because of its strange request. But I would like for you to provide me a plan. So what I mean is an algorithm. Describe to me a process that would allow me, based on your rules, to construct a group that has any given number of actions. So what I mean is, give me an algorithm that if I want a group with 10 distinct actions, meaning that even if I do all the compositions of them, there's still only 10 distinct actions, I would like for you to give me an algorithm that will allow me to produce this. But your algorithm should be in such a way that if I didn't want 10, but rather I wanted 27, I could still use your algorithm and obtain that result. All right. Now, 2.10 is actually something very important, albeit maybe strange. So the rules that we were given would not make any sense without 2.5, which was the rule that said there's a predefined list of actions. I can't talk about actions if I don't somehow have the original set on which I'm allowed to manipulate. So the other rules, however, are not needed in the sense of I could have axiomatically constructed something that did not have those 3 rules, potentially, let's say. So here's what we want to do. We want to determine whether or not the remaining 3 rules is redundant. So the idea is if somehow a combination of rule 2.6 and 2.7 implies 2.8, then clearly 2.8 is not needed. It's implied. So what we want to do is see if there are any situations where one of the rules is not satisfied while the other 3 are. So that's what you're supposed to construct. So for instance, in part A, the idea is you want to see whether you can devise a situation where you have a predefined list of actions, but we are violating rules 2.6 or 2.7 or 2.8. Right? And so remember, when you go back up, the idea is in part A, can we find something where the actions are not reversible? And you might say, that sounds strange to think about. Well, remember, you have the freedom to construct these actions yourself. So as long as you have a predefined list of actions where every action is deterministic and every sequence of consecutive actions is also an action, then you are able to do this. So you might say, well, what would be something that's not reversible? Well, it kind of depends. I'm not saying that this is an answer, but something that you could imagine is hitting a piece of marble with a hammer. I can hit the marble with the hammer. However, I cannot unhit it. I cannot replace that piece that I chip off. Now, of course, if you want to take my example, you would have to determine whether or not 2.5, 2.7, and 2.8 are true. But I'm trying to show you that there is a conceivable action that I cannot reasonably reverse. Similarly, I think we can easily come up with things that aren't deterministic. For instance, anything with gambling or related to that is never deterministic. And of course, if I give you a predefined list of actions that somehow do not combine well, it's very easy to violate Rule 2.8. So your goal here is to construct something that satisfies, or let's say satisfies 3 of the 4 properties. All right. Then 2.11, I want you to consider the idea of picking an integer. So randomly choose your integer. And I would like you to add any integer to the one that you chose. All right. So what I mean is if you pick the number 5, then I can add 1, or I can add 12, or I can add 7, or I can add negative 32. All of these are an action by which I take my original randomly chosen integer and I am manipulating it with this action. So every time I act on it, I'm simply adding or basically adding some integer, whether it's positive or negative. So is it a group? Does it satisfy those 4 rules that we have laid out? If it's a group, is there a generator or generators that allow you to construct every possible action that you can conceive? So can I come up with a list of actions, meaning add a certain number or numbers, that simply allows me to construct every conceivable action, such as adding 17 or adding 18? Sorry about the dogs. And then finally, exercise 2.12 basically is asking you to consider the previous exercise in more detail. So if you have even numbers, am I able to add any possible integer to that? All right. So that's one way to interpret it. The other way is to, and which is really the way that I would prefer, is if you have even numbers and you're allowed to add even numbers, or let's say multiples of even numbers, is this a group? What about if we're only allowed to consider the whole numbers, or I should really say integers here, because technically, I guess, depending on how you define it, 0 is not a whole number. But if you're only allowed to have the numbers 0 through 10, is this a group? So meaning I have the numbers 0 through 10, I can only add numbers 0 through 10. Will this be a group? All right. So, and once again, I realize in looking at this, I have not corrected exercise 2.12, and I'll correct this and re-update the notes. But the idea is everywhere that you see whole number, you should change this to integers. All right. So in C, would the answer to the previous question change if we allowed all integers, but now we're allowed to multiply by the integers? And what would be the answer if we're only allowed to multiply by the numbers 1 and negative 1? All right. So I think these are some pretty simple objects to consider, and I think oftentimes the simple ones are the most confusing because we tend to doubt ourselves. But I hope that through this description of the video that you kind of have a better understanding of what I'm hoping for you to do here. Now 2.6, ignore this for now. 2.6 is something that's moderately more difficult, and for now we're going to hold off on it. Later we may come back to it, or depending on how everyone's grades are looking towards the end of the semester, I may even say something like, if you do 2.6, I'll give you extra credit or something like that. But if you're curious, you should be able to go through 2.6 and see that this game is nothing other than kind of like an advanced version of Rubik's Cube. And so everything that we did before still holds, except it just seems a little more complicated. So if you want to look through it, you can. However, the current homework assignment will not deal with Project 2.6, and the next homework assignment will not either. We'll go on to Chapter 3. So if you have questions about anything, of course, you should email me. I will update this exercise both on the assignment tab and also in the notes. You should always be using my Dropbox link of my notes because those are the most recent. But if you have any questions, please let me know.